Okay, so now we're going to talk about acids, bases, and neutralization reactions. Okay, so an acid, hopefully you remember this, is any substance that produces H plus ions. Okay, and so that's what acidity is based on. It's based on an H plus. Okay, now if you remember, so if we drew a little stick of a hydrogen atom, here's your nucleus. You got your one little proton inside your nucleus. You got your one little electron spinning around inside it on the outside. So that's a hydrogen atom. So an H plus means that this electron has been stolen off. So all that you really have left, this is your empty electron orbital. Here's your nucleus, and here's your little plus proton charge right in the middle. And so really all that's left of that hydrogen atom after this electron goes away is an H plus. And so it's a proton. And so a lot of acid-base chemistry is built around what we call protons. And we just use the word proton to say that it's an H plus ion. Okay, so that's where that comes from. So more to the point, acids are H plus donors. They give those things away to anybody in solution, and that's how that works out. Okay, yeah. We've got some common acids. We'll talk about what those look like in just a little bit. Okay, we have a phrase that we call monoproduct, which means it has one H plus ion to give away. Okay, so HCl, HBr, those are our monoproduct acids. We do have diproduct acids. And those can give away two H pluses. So carbonic acid, H2CO3 is an example, sulfuric acid, H2SO4. There is one triproduct acid, and that's going to be 3 protons to give, so 3 H pluses to give, and phosphoric acid is that example, H3PO4. More often than not, diproduct and triproduct are just wound up into what we call polyproduct, meaning many protons. So it's not a huge thing. We don't really have to worry about all of that, but that's really what it is. So that's the basic rundown of acids. Let's do a basic rundown of bases next, okay? Now, bases, on the other hand, these are substances that accept H pluses. Substances, yes. And so they are also known as proton acceptors. There's another way that we can think about it. But in this reaction, they also produce OH minus or hydroxide ion. Okay, and so that's what we're going to use as our basic metric for a base. Okay, now some bases do not contain hydroxide. So don't let that fool you. Okay, so the most common example of that is ammonia. So if I take water in the liquid phase plus NH3 in the aqueous phase, that is going to be in equilibrium with hydroxide ion, OH minus, aqueous, and ammonium, NH4 with a +1, and that'll be in the aqueous phase. Okay, and so because hydroxide, they don't have to necessarily contain hydroxide, but they do make hydroxide in a reaction, and that's what happens here. This goes after a hydrogen, and it steals it from the water, and it leaves behind and creates a hydroxide ion. And so that's one of the things that bases will do or can do as they are working through and doing their chemical reactions. Now, we have strong acids, we have strong bases, we have weak acids, we have weak bases. Okay, and so strong acids and bases are strong electrolytes. And so that means that those things break apart completely. And so those break apart readily making lots of ions. Okay. Now, a weak acid and a weak base then do not break apart as readily. And so, because they don't break apart as much, they have fewer ions in solution, and so they have a lower concentration of the things that make them acidic or basic in solution. Okay? They're also weak electrolytes because of the fact that they don't break apart quite as much. And that pen is going to die on me here, I can see. Okay? And so that's what weak acids and weak bases do. And so that's how we pay attention to that. So there you go. Now, we have a list of common strong acids that I want you to know. So here they are. Your common strong acids are going to be HCl, and that is hydrochloric acid. HBr is hydrobromic acid. HI is hydroiodic acid. Chloric acid is HClO3. Perchloric acid is HClO4. Nitric acid is HNO3. And the last one that we're going to talk about or make you memorize here is H2SO4, and that is sulfuric acid. Now, I did say the dreaded memorize word, and I'm sorry, but you probably should commit these to memory just because it's going to make things easier for you in the long run. The sooner that you have them memorized, the sooner that it's going to stick in your brain a little bit better, and the less you'll have to look up when you need to do them, okay? Yeah. Your strong bases that you're going to need to know. All right, so your strong bases are you're going to be your group 1 metal hydroxides. Okay, and so that's going to include lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide. Those are all going to be strong bases. Okay, they will break apart completely. So the other one that you should commit to memory are your heavy group 2 metal hydrides, or metal hydroxides, excuse me. Okay, and so when I say heavy, I mean calcium and down. So calcium hydroxide, and I mean strontium hydroxide, and I mean barium hydroxide. Those are the ones that are going to be strong bases and dissociate completely and therefore be strong electrolytes. And so those are the ones that you need to commit to memory. Okay, so these are pretty common. We're going to see a lot of those. We're going to see a lot of those, and there are other hydroxides that we're going to take a peek at as well. So those are the ones that I think you need to know. Now, I'm sure you remember something that we call the neutralization reaction. I hope you do, anyway. And so when you were freshmen, we called them acid-base neutralization reactions. That's exactly what they are, okay? And this is when an acid and a base react to make a salt and water. And really, this is a double replacement, or to use the other word that we have just learned, a metathesis reaction, because we're just exchanging ions to make two different compounds, okay? And so here we go. If we have hydrochloric acid, so HCl, and this is going to be aqueous, plus sodium hydroxide, and that is also going to be aqueous. So we have those two pieces. H and OH are going to combine to form water. I'm going to write it like this, which is the same thing as H2O. This is going to be a liquid because we can't have aqueous water dissolved in water because it's a liquid. It's something different. The reason I like to write it like this is because I can see that this H comes from here and the hydroxide comes from here. It just makes more sense. It's easier to balance. You want to write it that way, go ahead. You want to write it that way, go ahead. I don't care. Just, I don't know. This is why I do it that way, just so you know. What's left is a salt. So the cation and that anion come together, plus NaCl. That's a positive one, that's a negative one. So we circle crisscross applesauce. The formula becomes NaCl. And this is going to be in the aqueous phase because chloride ions always produce aqueous solutions. Okay. Now, there it is. That's the molecular equation. Okay. If we wanted to, and I want to, so we're going to do it because, you know, I'm kind of that guy. We're going to break this apart into our total ionic. So that's going to be H plus Cl minus, both aqueous, Na plus OH minus aqueous. It's going to make liquid water, and these two will be in aqueous phase. So when I remove the spectator ions and I write the net ionic equation, what I really have is H plus in the aqueous phase plus OH minus in the aqueous phase makes H2O as a liquid. So that's really what's happening chemically in this chemical reaction. And so that's what we would see in any net ionic equation of a neutralization reaction. Now, let's do another example. In this case, we're going to have magnesium hydroxide. This is going to be a solid. Okay, so magnesium hydroxide is actually aqueous, or it's insoluble, so it's going to be a solid in solution. But we're going to add that to an acid. We're going to make 2H plus, 2HCl. This will be aqueous. Now, when we do this, we're going to make magnesium chloride, MgCl2, and that is going to be in the aqueous phase, plus water, 2H2O as a liquid. Now, okay, so this is our molecular equation. I'm going to do the total ionic in my head. This doesn't break apart. This does break apart. This breaks apart. That doesn't break apart. And so now I'm going to write the net ionic. And so here's the net ionic equation for this. Okay, we're going to have the magnesium hydroxide as a solid, plus 2H pluses as an aqueous. The spectator ion, chlorine is a spectator ion, so it cancels off. We're going to have magnesium 2 plus aqueous, because it's going to now be floating on the product side, plus 2H2O as a liquid. Okay, and so just trying to show you that there are other outcomes here, and yeah, there's other outcomes with this. You're not always going to just have OH plus H plus making water. You might have other stuff there as well. And so that's all I was trying to illustrate with this example. sometimes these reactions will produce gases. And so what we're going to talk about now are double replacement or metathesis reactions that make gas. Okay, and unfortunately, this is one of those things that you just kind of got to commit to memory. And we'll talk about this a bunch. We're going to work through a bunch of this in class together. So, all right. If we have S2 minus ions, they will make hydrogen sulfide gas in the presence of an acid. Okay, so something to think about. If there is an acid present, it's going to make H2S gas. So what does that look like? It's going to look like this. So if I have 2 HCl in the aqueous phase plus Na2 sulfide in the aqueous phase, so we're going to have our exchange. So we're going to make H2S, hydrogen sulfide. It'll be a gas, and our other piece is going to be NaCl, and that'll be aqueous. And I got a double U, and now I think we're balanced. Okay, so this one is one that will make a gas regularly. So that one's something you want to think about. The other one that you want to think about is carbonates. So CO3, 2 minus, and bicarbonate, HCO3 minus. They will react with an acid. To make carbon dioxide gas. Okay, and so this is a pretty common reaction. This is actually so common that bicarbonate and CO3 are actually used in beverages. So whenever you open up a can of something that has fizzy bubbly stuff in it, be it a bubbler or a Diet Coke or a Mountain Dew or whatever, it's going to produce CO2 gas when you unpop the top, because that pressure is going to come out of solution. It's going to make a gas. Okay, so this is a little bit more complicated though, so we got to kind of do 2 reactions instead of just one. So hydrochloric acid plus sodium bicarbonate, NaHCO3. So this is baking soda, and that's baking soda and hydrochloric acid. So in this case, we're going to make NaCl. Okay, this is aqueous. This could be aqueous or it could be solid. Either way, it's still going to react and do the same thing. That'll make an aqueous solution, but it's going to make H2CO3, and that will be aqueous. Now, H2CO3 in the aqueous phase is immediately going to break apart into water, H2O, liquid, and carbon dioxide gas. Okay, and again, this is so common that when you have your fancy caffeinated, carbonated beverage in a lovely, lovely can, the way that we get the bubbles inside it is by the company that makes it puts carbonic acid inside it. They know as soon as you pop the top on it, it's going to break apart into water and CO2. And you know darn well that they've got the calculations calculated perfectly so that it makes exactly the right number of water molecules to make it taste exactly the way they want it to taste inside that container when you open it up. So, yeah, that's how this works. So that is the reactions that I want to talk to you guys about. And yeah, I'll talk at you later. Bye.